Namaskar. So, in last class we were discussing about the few major properties of the Laplace transform. So, in this class also we will continue our journey on discussing the few important properties of the Laplace transform. So, let us see what we discussed in the previous class related to properties of the Laplace transform. We discussed about linearity. So, in that we demonstrated that if the Laplace transform of f1t and f2t are f1s and f2s, so their linear combination like a1 f1t plus a2 f2t, if you take the Laplace transform of the linear term, you will get the Laplace transform like a1 f1s plus a2 f2s. Similarly, for scaling, the Laplace transform of f of a t will be nothing but equal to 1 by a into the Laplace transform of f t, where you will replace s by s by a. So, this would be Laplace transform would be nothing but the function of s by a. Now, in case of time shift, if your signal is shifting by some time say a, the Laplace transform of that function would be e to the power minus as into fs. So, these three we discussed in the last class. Now, let us talk about the frequency shift. Now, if fs is the Laplace transform of ft, then Laplace of e to the power minus at multiplied by ft would be, if you take that function inside the integral. So, this is basically the standard definition of our Laplace transform, that is integration between 0 to infinity function ft into e to the power minus st dt. So, instead of ft we will write e to the power minus at into ft. So, this will become ft into e to the power minus s plus a t dt. So, which is nothing but the Laplace transform having s being replaced by s plus a. So, you can say that in case of frequency shift, the Laplace transform of e to the power minus at ft can be obtained from the Laplace transform of ft by replacing every s with s plus a. So, this particular property is called as frequency shift or frequency translation. Now, let us take an example. Suppose the cos omega t is a function, then its Laplace transform would be s upon s square plus omega square. Similarly, for sin omega t, the Laplace transform is omega upon s square plus omega square. Now, if we use the shift property and we need to obtain the Laplace transform of the damped sinusoid, that is damped sine and cosine functions, means we are multiplying cos omega t and sin omega t with e to the power minus at, then its Laplace transform can be given by simply replacing s, that is there in the Laplace transform of cos omega t, we will replace s by s plus a. So, in numerator we will replace s by s plus a, in denominator it will become s plus a whole square plus omega square. Similarly, in case of e to the power minus at sin omega t, it will become omega upon s plus a whole square plus omega square. Now, let us talk about the time differentiation. If fs is the Laplace transform of ft, then we need to find out the Laplace transform of its derivative, that is the Laplace transform of df by dt. So, we use the standard definition of Laplace transform, the integral from 0 minus to infinity df by dt e to the power minus st dt. Now, how you will solve this particular type of integral? We will use the integration by parts method. What does this method says? Suppose there are two functions u and v. So, integral of u v dx can be given as u into integral of v dx minus integral of derivative of u, in bracket it is the integral of v dx and multiplied by the derivative of u and the integral of v dx, and then the combined function will be having the integral with respect to x again. So, this is the property of integration by parts. So, the same property we will use for finding out the integral of this particular equation. So, here we will assume u is nothing but e to the power minus st and v is df by dt. So, then Laplace of df by dt can be given as, so you will take first the derivative of, you will take out, that is e to the power minus st is out, and then v dx integral, that will simply become ft, and the integration will be calculated between 0 minus to infinity. Then the second one, you will integrate between 0 to infinity, u dash, that is du by dt is given as minus s into e to the power minus st, and then again integration of v dx, integration of v dx would be nothing but function ft, and then the integration point, that is dt. So, now if you see this particular expression, when the value is infinity, this term will become 0. So, the whole function will be 0. So, at infinity the value will be 0. For 0, the e to the power minus st will become 1. So, at 0 the value of function at 0 will be the value, plus, because minus s you can take it out because s is constant when you are integrating with respect to t. So, this will become plus s, and then within the integration what term you are left with is ft e to the power minus st dt, which is nothing but the Laplace transform of function ft. So, finally, what we get from here is the Laplace transform of df by dt is nothing but sfs minus the value of function at 0, that is just before 0. So, now similarly you can take the second derivative of ft also. So, what you will get in case of the Laplace transform of d2f by dt2, you will get s square fs minus s, the value of function at 0, minus derivative of f at t is equal to 0. So, this is what you get for second derivative, Laplace of the second derivative of the function. If you continue in this manner, you can create more generic Laplace transform, that is for nth derivative of ft, which you can write as Laplace of d2nf by dtn is nothing but equal to s to the power n into fs minus s to the power n minus 1, the value of function at 0, minus s to the power n minus 2, the value of derivative, that is first derivative at 0, and so on up to the value of derivative n minus 1 at derivative at 0. So, this is your generic expression for finding out the Laplace transform of d2 and dnf by dtn. Now, let us talk about the time integration. Now, if fs is the Laplace transform of ft, then Laplace transform of its integral. So, let us take the function that is now integral of ft dt. So, when you use the standard definition of Laplace transform, this will be the integration between 0 to infinity, then function is here 0 to t integral fx dx. So, multiplied by e to the power minus st dt. Now, you will use again the same property, that is integration by parts. Let us assume u is nothing but 0 to t f x dx and v is e to the power minus s t. So, when you use the integration by parts property, you will get the function, that is 0 to t f x dx into 1 minus s e to the power minus s t, that is the integration of e to the power minus s t, and then the value between 0 to infinity minus 0 to infinity minus 1 by s e to the power minus s t into f t dt. Now, if you see carefully this particular expression, what you will see, when the term t tends to infinity, let us talk about the first expression, which first term which you have in this expression. So, if t tends to infinity, then this value will tends to 0, and again when it is when time t is equal to 0, this integration will become integration between 0 to 0 f x dx, which will again be 0. So, it means that this particular term, that is first term of the expression, is 0 between both of the limits. So, we can ignore this particular term. So, finally, what we left with is the integration of the Laplace of integration between 0 to t f t dt is nothing but 1 by s 0 to infinity e to the power minus s t f t dt, and this is nothing but the Laplace of f t. So, what we get finally, that the Laplace of the integration between 0 to t f t dt is nothing but 1 by s f s. Now, let us talk about the frequency differentiation. Now, if f s is the Laplace transform of f t, so that is by its standard definition you can represent f s is nothing but 0 to infinity f t e to the power minus s t dt. Now, if you take the derivative of function f s with respect to s, what you will get? So, if you differentiate both sides, the df s by ds will become, here if you differentiate, it will become 0 to infinity minus t, because now you are differentiating with respect to s. So, it will become minus t f t e to the power minus s t dt. So, which is nothing but the Laplace transform of the function minus t f t. So, what you can write, that Laplace transform of t f t is nothing but equal to minus of the differentiation of Laplace transform f s with respect to s. So, more generic you can write, like if you are taking the Laplace transform of t to the power n f t, its Laplace transform would be minus 1 to the power n d n f s by d s n. So, this expression will give you the frequency differentiation property. Now, let us talk about the time periodicity. If a function f t is a periodic function, which is shown in the figure, it is periodic with period t. So, it can be represented as the sum of time shifted functions. How? Let us see in the next slide. So, if you have this particular function, you can divide this the periodic function into 3 parts. So, one is say f1 t, which have a period between 0 to t, second is f2 t, which has a period between t to 2t, and third is having the period between 2t to 3t. Now, if you are compiling the function f t, you will say that this is a summation of f1 t plus f2 t plus f t 3, or if it is continuing, then so on. So, what you will write? You can simply write in terms of the step functions. So, you will simply write f1 t as f1 t, but f2 t you can write f1 t minus t, that is the time shift function, that function f1 is shifted by time t into unit step function t minus t. Similarly, For f3 you can write f1 t minus 2t, because it is a time shift function with time equal to 2t. So you can write f3 also in terms of f1 and so on. So for f1t, what is f1t? f1t is nothing but the function ft with limited the period, that is limited by ut minus u t minus t. So now if you are asked to find out the Laplace transform of the periodic function, that is fs, what you will write? You will write the Laplace transform of function f1t, that is f1s. Then we will use the time shift property, and we will write the Laplace transform of the second term, that will become f1s e to the power minus ts. For third term it will become f1s e to the power minus 2ts, and so on. So what will happen? You will finally get one expression which is f1s, and within bracket you will get 1 plus e to the power minus ts plus e to the power minus 2ts, and so on. So now if you sum up the series, that is 1 plus x square plus x cube and so on, the value of the sum of this particular series is 1 upon 1 minus x, provided the mod of x is less than 1. So now if you use this particular property, you can simply write the value of fs, that is the Laplace transform of a periodic function. What we can write? We can write fs is nothing but f1s upon 1 minus e to the power minus ts. So what we can observe from this? We can observe that f1s is the Laplace transform of f1t, that means it is the Laplace transform of function defined over its first period only. Now what we get is the f1s. If you want to find the value of fs, that is the Laplace transform of complete periodic function, so what we have to do? We have to multiply with the value of 1 upon 1 minus e to the power minus ts with f1s, then we will get the Laplace transform of complete periodic function. Or we can say that if we divide the f1s by 1 minus e to the power minus ts, we will get the value of Laplace transform of a periodic function. Now let us talk about two important properties, that is basically we will say as initial value and final value theorems. So these two theorems are very important in finding out the initial and final values of function. So that means this allow us to find the value of function at time t is equal to 0 and the value of function at infinity, and we can find out these two values directly with the help of Laplace transform of ft, that is fs. How we will get? Let us try to understand. Now let us take the differentiation property of the function, that is the Laplace of df by dt. So what we write? We write Laplace of df by dt is nothing but sfs minus the value of function at 0. Now if we let s tends to infinity, then the integrand in the above equation will vanish because of the damping exponential factor. So if you put the value s as infinity, this will become 0. So the whole of the expression to the right of Laplace of df by dt will become 0. So when it will become 0, you can simply write it as limit s tends to infinity, s of fs minus the value of function at 0 equal to 0, or you can write, because this value will be a constant value, so you can simply write limit of s tends to infinity, s f s is the value of function at time t is equal to 0. So this particular property is known as the initial value theorem. Now, in case of final value theorem, let us take the same property of the Laplace transform for the df by dt. So, Laplace of df by dt is nothing but sfs minus f0. So, that is nothing but the value of the integration between 0 to infinity df by dt e to the power minus st dt. Now, if s tends to 0, what we can write? Limit s tends to 0, sfs minus f0 equal to 0 to infinity df by dt e to the power 0 t. So, this will become now 1. So, that means you can simply write this particular expression is nothing but integration between 0 to infinity df, or you can write the value of function at infinity minus value of function at 0. Now, you have value of function at 0 at both sides, those both will cancel out. So, finally, what you will get, the value of function at infinity is nothing but limit s tends to 0 s fs. So, this particular expression is called as a final value theorem. So, if you compare both of them, here when s tends to infinity, the value of function s fs will give you the initial value, while in case of final value f infinity, the limit will tends to 0 and you will find the value of function s fs when limit s tends to 0. So, you can simply remember it by understanding that when s is tending to infinity means the value which you will get will be at origin, and when s tends to 0, the value which you will get for the function is at infinity. So, these two are very important theorems, but the final value theorem has its own limitation. What are those limitations? The final value theorem will be valid only when all poles of fs are located in the left half of S plane. What do you mean by poles? Let us take this particular function that is the Laplace transform of e to the power minus 2t sin 5t. So, here if you are asked to find out the poles of fs, what you will do? You will simply take the denominator and equate it to 0, and you try to find out the roots of this particular expression. So, since it is a second order equation, you will get 2 roots of s. So, those 2 roots will be nothing but the poles of fs. So, what you need to do? You have to observe whether the value of those roots are having any negative real part or not. If poles are having negative real part, then only you can apply the final value theorem in the function fs. The only exception in this case is the case when fs has simple pole at s is equal to 0. Means if this expression is having another component like 1 by s, then you will have one pole at s is equal to 0. So, that is the only exception in finding out the final value theorem. So, these two things you have to always keep in mind when you are asked to find the value of final value of the function f t, that is f infinity. Now, let us take the example. The function is f t e to the power minus 2t sin 5t. Its Laplace transform would be 5 into s plus 2 whole square plus 5 square. So, the final value theorem, if you apply, the value of f at infinity will be 0, because limit s tends to 0, 5 s divided by s square plus 4 s plus 29 will be 0. and this is what you can see from the function f t also, because you have a exponentially decaying component with the function. So, final value will always be 0. Now, let us take another example. Let us take the function is sin t. So, its Laplace transform would be f s is equal to 1 upon s square plus 1. Now, if you apply final value theorem, limit s tends to 0 s f s, you will get the value 0, but this is wrong. Why? Because function f t, that is sin t, will always oscillate between plus 1 and minus 1, and it will not have limit as t tends to infinity. Now, the final value theorem cannot be used in this case, because if you take the poles, that is the roots of this particular second order equation, you will see the poles has the value s equal to plus minus j, which are not in the left half of S plane, because these two poles does not have any negative real value. So, that means that in this case you cannot apply the final value theorem. So, you have to always keep in mind where you can apply the final value theorem, where you cannot use the final value theorem. So, you can summarize that the final value theorem does not apply in finding the final values of sinusoidal functions, because these functions are oscillatory in nature and does not have the final values. Now, initial values and final value theorems shows the relationship between origin and the infinity in the time domain as well as in the S domain, and these two theorems also serve as a useful check on Laplace transform. So, now let us see few of the example, so that we can understand what we discussed till now more clearly. Let us see, there is function f t, which is a combination of unit impulse, unit step, and the exponential function. So, what you will use? You will use linearity property here and find out the value of the Laplace transform of f t. So, let us apply the linearity property. The Laplace of delta t will be 1, Laplace of the 2 you can take out, Laplace of u t will be 1 by s, and then the Laplace of e to the power minus 2 t will be s 1 upon s plus 2. So, now you know the Laplace transform of all these three terms. You will simplify, then you will get the Laplace transform of complete function f t, that is s square plus s plus 4 divided by s into s plus 2. Now, let us take another example. If function f t is t square sin 2 t multiplied by unit function u t. So, now what we know is that the Laplace of a periodic function, that is sin 2 t, is nothing but 2 upon s square plus 2 square, that is omega upon s square plus omega square. This is what we know about the Laplace of sine function. So, this will become 2 upon s square plus 2 square. Now, what you have to do? You have to use the frequency differentiation, because you have a t square term. So, what you have to do? You have to double differentiate this particular term, that is 2 upon s square plus 4. So, and then multiply by minus 1 whole square, and then when you simplify, you will get the value of the Laplace transform of t square sin 2 t, and what we get is 12 s square minus 16 upon s square plus 4 whole cube. Now, next is, if we are asked to find the Laplace transform of a gate function. So, what we can see here, this is a gate function which starts from 2 and completes at 3. So, you can say that this particular function is combination of two unit step function. How? You can say this function gt is nothing but 10, because 10 is the amplitude, multiplied by unit step function u delayed by 2 time periods. So, u t minus 2. So, you can say there is one function like this, and minus of u t minus 3 means there is another function which is like this. So, when you will say, when you combine both of them, minus of u t minus 3 you can write. So, what you will say, that the Laplace transform of u t is a combination of two unit step function, one is delayed by 2 time period and the second is delayed by 3 time period. So, what you can write now, you can just take the Laplace transform of both of the unit step function delayed by their respective time period. So, the Laplace transform of gt will become gs, that is nothing but 10 into e to the power minus 2s by s minus e to the power minus 3s by s. When you simplify, you will get the value of gs, that is 10 by s e to the power minus 2s minus e to the power minus 3s. So, now with this we can close our today's session. In this session we discuss about various properties of the Laplace transform, and the next class we will discuss about the calculation of inverse Laplace transform. Thank you.